Okay, so on Friday I introduced you the new exponential relationship, where the relationship that exists between the x and the y variables have a common ratio rather than a common difference. Now we're getting into the actual, those were real life application questions where your starting point was the y-axis. We didn't really see a complete exponential graph with the ones that we did on Friday. Now we're going to get into what does a proper exponential function look like. So the first one we always start with is 2 to the power of x. There we go. So when you graph 2 to the power of x, you should notice that y-intercept is at 0, 1. Why is the y-intercept at 0, 1? Any thoughts why the intercept will be at 0, 1?
Because when x is 0, we're going to be exponent of 0, which is not 1.
Correct, right? X is your exponent, right? 2 to the power of x. X is now the exponent in exponential functions. And when x is 0, we have an exponent rule that says any exponent to the power of 0, the base equals to 1. So in a situation where your base could be any number, that base to the 0, your y-intercept should always be at 1, unless you're moving the graph around, which we'll do in a few minutes. So you're clicking on the graph. What do you notice when you move to the right of the graph? So as x gets bigger, what happens to the graph? What was y doing? As x gets bigger, your y increases, also gets bigger. When x moves to the left, so when x is getting smaller, what do you notice? Y gets smaller. And y gets infinitesimally smaller. I know on the graph, at some point it starts saying that y is 0, but that's not real. That is because the program is only programmed to a certain number of digits, and once you surpass that, then it just rounds to 0. But what's happening here is that your graph, the y value, is just getting smaller and smaller and smaller. Right? We know when your exponent is negative, that changes your base to a fraction. So if the x is x to the negative, if you're doing to the negative 10, that means you're really talking about the fraction 1 over 2 to the 10, which is 1 over 10, that 1 over 10, 24. If you were to go even higher, 2 to the power of negative 20, that's going to be 1 over 2 to the negative 20, which means the denominator in the fraction is getting larger and larger and larger and larger, which means the fraction itself is getting smaller and smaller and smaller and smaller. But it's never going to reach 0. Why will it never reach 0? Will 2 to the power of x ever equal 0? No. Why not? I say so? Because it's not possible. Your base is 2. What you're saying is there a way that you can multiply 2 however many times and the answer is going to be 0? Is that even possible? No. Because the only way something can equal to 0 is if you multiply that something by 0. And when you're talking about exponents, that doesn't happen. Right? 2 to the power of 4 is 2 times 2 times 2 times 2. Even if you're doing 2 to the negative 4, that's 1 over 2 times 2 times 2 times 2. There is no 0 in that situation, so you can't get to 0. What it will do is get smaller and smaller and smaller, so it will approach the 0, but never actually get there.
I was just kind of wondering about this, but how come when something's to the exponent 0, it equals 1?
Why didn't you ask that when we were doing exponent rules?
I'll just think about it right now.
Okay, a little diversion. What is 2 to the power of 2 divided by 2 to the power of 2? Right? Exponent rules tell us we subtract the exponents, so we get 2 to the 0. Right? Yes? But we also have a rule that says when you divide 2 to the 2 is 4 divided by 4. 4 divided by 4 is 1. 2 to the 0 is 1. Okay? Anytime you divide a number by itself, the answer is 1. But our exponent rule tells us that that ends up being an exponent of 0. So that's where our logic comes in and says, okay, that means anything to the 0 must equal to 1. Is that okay, Ryan? Okay, no problem. Let's get back to the graphs. So as you recall from chapter 1, we talked about situations where if you have a graph that approaches a line, that we call that an asymptote. We saw those when it came to rational functions. We have an asymptote now for the exponential function. And that would be our parent graph. In our parent graph, that asymptote is the x-axis. Your graph approaches y equal to 0, but never actually reaches it. It just gets smaller and smaller and smaller and smaller and smaller, but never touches it. So, where rational graphs had both a vertical and horizontal asymptote, exponential graphs only have a horizontal one. Okay, we don't have vertical asymptotes for exponentials, we just have this horizontal one. Good so far? Let's continue. So, as we already said that when x is increasing, our function is also increasing. Oops. Now, our domain and range should be, I should ask before that, but I'm showing you. The domain is very easy because you have negative values of x, you have positive values of x, that your domain for x is all real numbers. Your range, however, because of this asymptote, is any numbers greater than 0. So your range is all real numbers greater than 0. In this circumstance, y is never going to be a negative number because the asymptote prevents us from going below it. Now, should we move our graph around, then we can get negative y values, but we're always going to have some asymptote that you can't go below. Or above if we reflect it, which we'll do in a few minutes. Questions so far? I don't know if you got to this point or not, but if you graph 3 to the x, 5 to the x, 10 to the x, what should you notice?
It's getting wider.
3 to the x, 5 to the x, and 10 to the x are getting wider?
On our graph on the right side, it's opening up one.
Are you sure? Or were you graphing the fraction? Because it should be the opposite.
Oh, so here's the wrong one, yeah.
Oh. It gets narrower, right? When you increase your base, your graph should get narrower, which means the curve of the exponential becomes more pronounced the higher your base is. And I don't necessarily want to say that it's a 90 degrees, but the higher your base, the more perpendicular the curve looks. It's not perpendicular. You'll never actually get a complete perpendicular curve, but the higher your base, the more perpendicular it is. Okay? So if you see, I don't know if you can see this or not, the purple one is 10 to the x, and you definitely have a more perpendicular curve than the 2 to the x, which is the red. Imagine if you were to graph something like 200 to the power of x. That would definitely have a more perpendicular curve. Not that we ever would, but say if you were graphed 1,000 to the x, that would definitely look very perpendicular-like. But it's never actually perpendicular, okay? So yes, you should notice as you increase the base, your graph becomes more narrower. Oh, that's not what I'm talking about. The steeper the curve becomes. They all share the same y-intercept. They're all increasing functions. Everything is basically the same. When you have 3 to the x, 4 to the x, 5 to the x, 6 to the x, as long as you have a whole number base, you have an increasing function, greater than 1, I should say, then all of these will be the same. Y-intercept 0, 1, domain is XCR, range is y greater than 0, asymptote is the x-axis. Yeah. This is a new parent function, yes. Nice thinking back from chapter 1. But technically, all bases are their own parent function. So 2 to the x is its own parent function to 3 to the power of x, 10 to the power of x is its own parent function. Each separate base is technically its own parent function, but they're all still under the exponential family.
And all of the like the 7 to the x and the 10 to the x, they all have the same domain and range.
They all have the same domain and range. Until we move the graphs around, the domain and range and y-intercept and asymptote all fit the same. All that's changing is the base, which means the graph is steeper, but everything else stays relatively the same. Well, it stays the same. So far, so good? Now, I don't know if you got a chance, if you didn't have enough time to graph now, what happens if your base is between 0 and 1? All of these bases we've just done were bases greater than 1. What happens when your base is between 0 and 1? Do you want a few minutes to do that on your own, or do you want to do it in class? Do it together, okay. So let me show you what these graphs look like. So these are your graphs when your base is a fraction. So the red is the 1/2 to the x, the blue is the 1/3 to the x, the green is 1/5 to the x, the purple is 1/10 to the x. What do you notice between the two sets of graphs? They're the reciprocal. Okay? Your bases are the reciprocal. Your graph is identical except that it's now decreasing to the right. Whereas when your base is a whole number, it's increasing to the right. When your base is a fraction, between 0 and 1, it's decreasing to the right. They're the reciprocal. They're the mirror image of each other. So if you were to graph the 2 to the x and the 1/2 to the x in the same graph, the y-axis is its mirror reflection. They are a reflection of each other across the y-axis. So, same y-intercept, which again, same rule. X is 0, 0, anything to the exponent of 0 is 1. So regardless of the fact that our base is now a 1/2, a 1/3, a 1/4, a 1/5, whatever, because the exponent is 0, that's going to work out to 1. As x gets bigger, the y value is now decreasing. So it's getting closer and closer and closer to 0. Again, infinitesimally closer, but never actually reaching the 0 mark. It just gets smaller and smaller and smaller. When x is decreasing, so moving to the left, as we get smaller values of x, the graph is increasing. When your base is between 0 and 1, we call those decreasing functions. I think on Friday I used the term decay. They're decaying functions. Again, like increasing or growth, decreasing or decay. You'll notice domain and range is still the same. Range, the domain, all real numbers, because you can have values of negative x, you can have values of positive x, so you use all values of x. But your range, because of the same asymptote, is restricted to being above 0. And you'll notice that the same thing applies. As I increase the denominator in our fraction base, the steeper the graph becomes. Which makes sense when you increase the base, when you increase the base in whole numbers, the steeper it is. Now, when we increase the denominator in our fraction base, the steeper it will become. Exponential graphs never loop back up like a parabola would. Okay, if you notice that these are the two basic shapes that exponential graphs have. You either have a continually increasing graph or a continually decreasing graph with the asymptote from either one. Questions so far? Move it up a little? Like, to see this part?
Not just like the top part.
Oh, huh. Well, what have you been doing, Ryan?
No, I just didn't get the like last few words.
Okay.
It's fine.
Okay, are you almost done?
Oh yeah.
Okay, so just to finish off characteristic-wise, I already showed you the two graphs. So, your basic characteristics of this exponential graphs, you'll notice in all instances the base is positive. You never graph, or really it's not possible to graph negative bases. Why would it be impossible to graph a negative base? You should picture how you would graph a negative base. Say, for example, I tried to graph bracket negative 2 to the power of x. What would that look like? You can try it on the graph computer, but it's not going to do for you. Because it's... Lucan,
Would it be reflected on the x-axis?
would it be reflected on the x-axis? Not really. What's the problem with a negative base? Okay, let me ask you this. If you have a negative base and an even exponent, what happens? It becomes positive. Your answers are all positive. But if you have a negative base and an odd exponent, what is your answer? It stays negative. So picture this. So negative 2 to the power of 0 would be what? Negative 2 to the power of 1, negative 2. Negative 2 to the power of 2, positive 4. Negative 2 to the power of 3, negative 8. It goes back and forth between a positive and negative. It oscillates, which is very complicated. So that's why we don't graph those in terms of negative bases. It's a very complicated type of graph since your answers oscillate positive to negative, positive to negative. Okay? That doesn't mean you're never going to have negatives in your question because that's what we're going to do in a few minutes. If you recall, we did deal with transformations with negative numbers, say a negative a coefficient that resulted in reflections. So it's not like you will never get negatives, it's just that the base itself won't be the negative one. Okay with this? So this is all the characteristics. Positive base, your graph is increasing when the base is greater than 1. Your graph is decreasing when the base is between 0 and 1. Y-intercept is always 0, 1 for these parent graphs. Domain is all set of real numbers. Range is always greater than 0. Horizontal asymptote at 0. Y is equal to 0. These are all the same characteristics for your base parent graph. The only thing that changes is the base. Did I already ask you before? I forget. What if your base was 1? Aldrich? What type of line? It would be a horizontal line. Your base can never be 1 because you just have a horizontal line. Because 1 to the power of anything is 1. So if you were to graph 1 to the power of x, you'd just be drawing a horizontal line with y is equal to 1. So far so good with these are parent graphs. Good. Now guess what we're going to do? Move them around. Because that's what we like to do. So jump to page... Oh, I don't know why this is in the wrong order. For that, I apologize. Jump. Okay. Page 13. I forget. Okay, so now we're going to transform all of these wonderful new exponential graphs. You'll notice the setup is identical to the transformations we talked about in chapter 1. The identical. We have the A coefficient. Let's recall, what does the A coefficient do? Wasn't that long ago? What did the A coefficient do? Stretch or compression in which direction? No. That was vertical. Okay. A was your vertical stretch or compression, and it reflects across the x-axis. What was the B transformation? Horizontal stretch and compression and reflection across the y-axis. The H transformation was
Sorry, left to right.
horizontal translation, moving it left and right. And the K transformation was moving it up and down, correct? Right? Same thing as what we did in chapter 1. The only thing that's now changed is our function that we're transforming. We're now going to be transforming the exponential functions. But we're going to do it the exact same way we did it in chapter 1. We're going to use our mapping notation to do it. So remember that B and H, because they're transformations affecting the x coordinate, happen opposite. So when you're multiplying B, it's a division of B. If you're dividing B, it's a multiplication. And then if the H is always opposite as well, if it's subtraction, it becomes add. A and K are values that affect the y coordinates, stay the same, nothing happens with them. People remember this? Yes? Let's do an example. So I have the graph h of x is equal to 2 to the x. These are the coordinates for the parent graph. When x is negative 2, y is a quarter. When x is negative 1, y is a half. 0 is 1, 1 is 2, 2 is 4. I forget what that question is asking of me. We want to transform it by adding 2x plus 4, which means what's going to happen? What should happen? It's going to move up 4 spaces. So in terms of the mapping notation, that's k. We're just adding 4 to the y value. So you should get that. 2x plus 4 means we're adding 4 to our y value. Our x value stayed the same, negative 2, negative 1, 0, 1, 2. Our y value is going to add 4. I know you have fractions, but again, deal with them. You're doing a quarter plus 4 works out to 17 over 4. A half plus 4 is 9 over 2. 1 plus 4 is 5. 2 plus 4 is 6. And 4 plus 4 is 8. So your graph should look like this. Like that. Don't ignore the red. Right? So you'll notice we have moved the graph up 4 spaces, which means what's our asymptote now? At 4. The asymptote is whatever your k value is. I want you to graph the other one on your own. Again, 2 to the power of x. We want to graph 2 to the power of x minus 3. What should that graph look like? And yes, if you must, you can change it to the decimal, but really you shouldn't have to. Everybody done? Still working? Shouldn't be that hard. We're just moving it down 3 spaces. By the way, to graph these, I would never suggest, I always graph the whole numbers that are proper points, and then you identify where your asymptote is, and then you can fill in the rest of the curve. I don't really expect you to graph the fraction points. Identify where the asymptote is, plot the whole number points, and then just finish the curve knowing that it's just going to approach the asymptote. That's how you should graph it. These are the values I got for y. We're taking y and subtracting 3. So a quarter minus 3 is negative 11 over 4. A half minus 3 was negative 5 over 2. 1 minus 3, negative 2. 2 minus 3, negative 1, and so on.
Hey, is this your test here with the happy Halloween on the bottom like that? It is? Yeah, who did that? So we need to figure out who messaged this, and she's gonna get a 0 as well. So during period 2, somebody took a picture of the whole test.
It's literally a great friend. Take you on to the
How do they know this? What do you mean take one?
Who sent you that?
No one's getting anything.
How do you know? How do they know that? How do they know this?
How do they know this information? Somewhere.
Oh, yeah, literally.
Yeah.
Let's do a real one.
People, continue working.
No, that was the other guy. Actually,
Oh, jeez. Okay, where were we?
Miss, what happened?
Student photocopied the text we had this morning.
Photocopy?
Well, not, sorry,
Oh, okay.
use their cell phone.
Miss, how do you figure that out?
I don't know, Miss Costigan saw the cell phone.
Oh.
Let's go through this. So, back to the first graph to the x plus 4. You'll notice domain hasn't changed. And technically, is there any transformation that we can do that will change the domain of exponential graphs? No. You can multiply this, you could shrink it, we could even reflect it. But in terms of our x will always be all real numbers. Your domain for exponential graphs should never change. Always x real numbers. What changes is the range. And our range is going to change based on whatever our k value is. So you see in the first graph, we added 4, our range became greater than 4 because that was what the asymptote was. The second graph, we subtracted by 3, which means our range is now y greater than 3. Whatever your k value is determines your asymptote, which determines what your range will be. Are we okay with that? Your y-intercept will change. What's the matter, Christian?
Isn't the y-intercept 0 and negative 3?
For which one?
For the second one.
No. Because the original was 0, 1, and we brought it down 3 spaces, which would be negative 2.
Oh, my bad.
Okay?
Wait, do we have doubles on the list tonight?
Can we move on from this? Let's do another one. Now let's do the involve H. I'm going to change my base to 3 now. So now we're graphing 3 to the power of x. These are the parent coordinates for 3 to the power of x. Negative 2, 1 over 9, negative 1, 1 over 3, 0, 1, 1, 3, 2, 9. These should be, I don't expect you to memorize these numbers. These should be easy to come up with. Okay, you know what, based on the base you have, you know what your parents, you can easily find these. If you want to take the time and memorize these parent things, that's fine, but they should be easily to come up with. You'll notice in g of x, we're now graphing 3 to the power of x minus 2, which is now the h transformation, which is affecting the x coordinate, which happens opposite. So in our mapping notation, we're adding 2 to the graph. Our y values will stay the same, 1 over 9, 1 over 3, 1, 3, and 9, but our x coordinates are now going to add 2. So we end up getting 0, 1, 2, 3, and 4. Which means this graph is being moved to the right 2 spaces. To the right, 2 spaces. And again, I don't expect you to graph the 1 over 9 and the 1 over 3. What I expect you to do is graph the 2, 1, the 3, 3, the 4, 9. Identify your asymptote, which in this case is the horizontal. So plot in your horizontal asymptote and then just draw the curve to run along that line. Please make sure your graph does not cross the line. I know it can get very tricky because even this graph right here looks like it's right on it. As long as you're not crossing the line when you draw it, I will not take marks off. But if you draw the curve that looks like it's crossing the x-axis or whatever the asymptote is, I will take marks off. Just draw it so that it's running along the axis, the asymptote. Okay? We look at h of x. We're taking 3 to the x and we're adding 3 to the power of x plus 3, which means we're subtracting 3 in the mapping notation. Again, your y values stay the same, but your x is going to be minus 5, minus 4, and minus 3, minus 2. Because we're moving it, the graph 3 spaces to the left, and should look like our purple graph here. Does moving your graph left and right affect your asymptote? No. Only moving it up and down, though. Questions so far? Yeah.
So the numbers in the exponent represent the h now.
Yes.
So if we have
Yes,
an
if
h
you can-
value, it would be
Any number in the exponent will be your h value if you're adding it to the x, and then we haven't done it yet, but if you have a b term, it will be multiplying. Let's look at all of our stuff here. Again, domain for both of them are always extra numbers. Your domain never changes. Regardless of what exponential function you're dealing with, your domain will always be XER. And in this case, since we haven't moved the graphs up or down, our range number hasn't changed either, because our asymptote hasn't changed. Since our asymptote is both at 0, then our range is y greater than 0. Our y-intercept, however, has changed for the 3 to the x minus 2 Alright, y-intercept is now 0 and 1/9. And the y-intercept for the 3 to the power of x plus 3 is 0.27. I don't even think it fits the graph, no. Yeah, it didn't even show up. If your y-intercept doesn't show up in your table of values, how do you easily find it?
Substitute 0 into the x.
Correct. Just sub 0 into the x and solve. So this would have been, right? 3 to the power of x plus 3. If we sub 0 in for x, then what are we left with? 3 to the 3, which is 27.
Is that the same for, well, the other one was on there.
The other one we did see it on the table of values, but yeah, if you wanted to do it algebraically, just sub 0 in for x, which would have meant you had 3 to the negative 2, which is 1/9. Any questions about that? Okay, so far? Now let's do some stretching and compressing. Now please notice how the coefficients are the notation. When you have an a value, so you're stretching and compressing vertically, your exponential part will be in brackets. The x can go inside or outside the bracket, it doesn't matter, but the entire base, so like here we've got g of x is 2 times 5 to the power of x. You do not multiply the 2 and the 5 together. Proper bed math. Our new base here. When you get higher than a base of 3, I would suggest shortening down your parents to just -1 to +1. Because, I mean, -2, the answer is 1/25. Nobody plots that. So you could just stick to the, honestly, even if you want to do for base 2 or base 3, if you want to just stick to the -1 to +1, I'll be fine with that. Okay? Or at least just not do the -2. If you want to do a little bit more on the positive side, that's okay. But the higher the base, the bigger your numbers for y, and I would not play that. Like when x is 2, y is 25. I'm not going to give you a graph that goes all the way to 25, so it's pointless to even do that one. We're multiplying our function by 2, so that means all y values get multiplied by 2. X stays the same, 1/5 becomes 2/5, 1 becomes 2, 5 becomes 10. Notice, again, we're not moving this graph up and down, or the horizontal aspect stays the same. But our y-intercept has doubled because our a coefficient was 2. In the other example, we're multiplying a by 1/2, so we're compressing it. Again, your x values stay the same. We're just multiplying y by 1/2. So 1/5 times 1/2 is 1/10. 1/5, 1 times 1/2 is 1/2. 5 times 1/2 is 5/2. Again, if you must change that to a decimal to help you plot it, that's fine. But what you get is a slighter, more compressed graph, a little wider. Questions about A's? Again, A and K are always the easier ones because nothing changes when it comes to those. Domain should stay the same. Domain never changes. Nobody should get the domain wrong for exponential graphs because it never changes. Our range also is not changed because we haven't moved the graph up or down. The only way the domain is going to change, the range is going to change is if we're moving it or reflecting it, which we haven't done yet. Our y-intercept becomes 0, 2 and 0, 1/2. Asymptote stays the same at 0. As you go through these at home, make a note of what transformations affect each of these things. No transformation affects the range. Some transformations will affect the range. That's the domain. No transformations affect the domain. A couple transformations affect the range, along with the y-intercept and the asymptote. Questions about those two? A couple more. Now we want to do stretching and compressing horizontally. Again, notice, this is very important because people always get this wrong. Notice where the B is in your graph. Okay? The B is now multiplying your x. So here we've got 10 to the power of x. Our parent coordinates would be -1, 1/10, 0, 1, 1, 10. Here we want to graph g of x, 10 to the power of 2x. B, just like h, happens opposite. So because we're multiplying x by 2 in the equation, means we're actually going to multiply x by 1/2 in the mapping notation for the table of values. So -1 times 1/2, -1/2, 0 times 1/2 is still 0, 1 times 1/2 is 1/2. Y values stay the same. Technically what we have here is a compression. Compression horizontally. In our graph h of x, we're plotting 10 to the power of x over 2, which means in the mapping notation, we're multiplying by 2. Again, always opposite. Which means our x becomes -2, 0, 2. Y stays the same, 1/10, 1, and 10. Technically, this is a horizontal stretch. So again, imagine we're stretching this out this way. So the blue graph is wider. When we are compressing horizontally, the graph becomes narrower. When we are stretching it horizontally, it becomes wider. And you'll notice, did B change anything? No. B affected nothing. Everything stays the same. Domain was the same, range is the same, y-intercept and asymptote are the same. Your B value does not affect any of the characteristics of your graph. Right now, the only thing that has affected these values is the K. K is the only thing as of now that's actually changed any of our domain range. Well, nothing changes the domain, but the range, y-intercept, and asymptote. So K affects the range, y-intercept, and asymptote, and the A value affected the y-intercept. So far, those are the only things that have changed. Questions so far about this? Julie, was that a question? No?
No, sorry.
Okay. Hopefully all of this, again, this is not brand new stuff. With all of these transformations, we did a lot of them in chapter 1. The only thing is it's a new graph. Lastly is the reflecting. When A is negative, it's reflecting across the x-axis. When when B is negative, it's a reflection across the x-axis. Y-axis, other way around. I want to bring your attention. Okay, we'll do this one first. G of x, 2 to the power of -x. That's when x. So we're multiplying x by -1. So that becomes 2, 1, 0, -1, -2. So what we have is pretty much a reflection across the y-axis. So our graph looks like this green. Is there a different way we could write y is equal to y is equal to 2 to the -x? Is there another way we could write that? Brian? 1/2 to the x. y is equal to negative x is the same as y is equal to a half to the x. They are identical. So you could really write them in either way. Okay? They are technically the same graph because of our negative exponent rule. Same thing with if you had 3 to the negative x and 1/3 to the x, all identical. This is the reciprocal. Are you okay with that? Now, earlier I said bases can't be negative, and you look at h of x, and it says negative 2x. Is the 2 negative? No. Technically, again, brackets are very important. Technically, what's the negative? 1 is negative, right? Technically, h of x equaling negative 2 to the x is really negative 1 times 2 to the x. That's really what this is. We just don't write the 1. Okay? So I don't want to think that negative 2 to the power of x means the 2 is negative. It means it has a coefficient of negative 1. Okay, so you're going to multiply the y values by a negative 1. And what happens is that gives us a reflection across the x-axis. And this is the only time, what do we notice about the red graph? It's now below the x-axis. That's the only time that's going to happen. If you have an a coefficient that's a negative quantity, the entire graph gets reflected and is now completely in the negative region. Everything else, you're in positive. But here it's now going in the negatives. Which means what is going to change here for the red graph? Will our domain change? No. Will our range change? How will the range change? It's now less than 0 because our graph is now below the axis. We still have the asymptote at 0, but since the graph has been reflected, it changes the inequality to less than. Our y-intercept also now becomes negative 1. Because again, that whole reflection has happened. Yep. No, the asymptote is the line itself. So we say it's the y equals 0, that's the line. Just like when we were identifying the asymptotes in our reciprocal graphs, the same thing was the case. Like the asymptote itself is, say for example, we did y is equal to 1 over x plus 2. The asymptote itself is the line x plus 2 is the line x is equal to negative 2. That's the asymptote itself. The restriction for the graph is that x can equal negative 2. But the line that we're talking about is just the normal equation. Any questions about all this transformation stuff?
Wait, so our homework is from 4.5 and 4.2.
I don't know what is the homework look like.
That's like 6 worksheets.
Oh my lord. Oh. Why don't I have a homework log?
It's just one of the sheets because I'm not done.
What does your homework log say?
It's LP 7 to 9 and 17 to 19.
No, you're only supposed to do. No, 7 to 9 we just finished.
Wait,
Didn't we just do that? We already
was
did
that
7 to
the
9.
activity?
Yeah, that was the activity. We already did that. You're only doing the 17 to 19. Okay? Because we already did this. We started this already. Yeah?
Wait, how about part 2?
It's a page cut, right?
Right now.
Oh no, sorry. That's so wrong. You're only doing 17 and 18. Sorry. 19 is the next lesson. So your homework is page 17 and 18. There is no, well, we're going to do another day of transformations tomorrow, which is the textbook. So this is part 1 today, 17 to 18, and then tomorrow we're doing the textbook. 2 days. Okay? Everybody clear? Good.